The motivation behind this work was to improve excitation homogeneity in high-field simultaneous multi-slice imaging. The use of high and ultra-high field MR scanners provide benefits such as increased signal-to-noise ratio, higher pole sensitivity, and higher susceptibility contrast. But one of the major challenges at high field is the transmit RF field inhomogeneity or the B1 plus inhomogeneity. Just like in conventional single-slice imaging, images acquired using the SMS method suffer from center brightening and shading artifacts caused by the inhomogeneous RF field. To solve this problem, we propose a method to design multiband spokes pulses that excite and compensate for B1 plus inhomogeneity in multiple simultaneously excited slices. The pulse design method is summarized in the method figure on the bottom left of the slide. First, a conventional single-slice selective pulse designed using the SLR algorithm is phase modulated to produce pulses that excite NSL number of desired slices. Each of the NSL pulses is then copied for the NS number of desired spokes. Now, the goal of pulse design is to optimize the amplitude and phase values, together called the RF shim values, of each of the NS times NSL number of pulses. And for all the slices, jointly optimize the placement of the spokes in excitation k-space, which corresponds to optimization of the excitation k-space trajectory traversed by the multiband spokes pulse. To reduce the overall peak power of the spokes pulse, optimal slice phases were determined. After the RF shim, slice phases, and k-space trajectory are optimized, the pulses are summed across the slices to produce NS number of spoke subpulses. The figure shows a 5-spoke multiband pulse. This train of shimmed multiband pulses, along with the optimized spokes trajectory, together form the multiband spokes pulse. The results figure on the right side of the slide shows in vivo images acquired in one of the subjects using a 7 Tesla MR scanner. The B1 plus maps measured in 3 slices using a birdcage coil show the typical amplification of the transmit RF field near the center of the head. The top part of the figure shows the acquired images and flip angle maps measured using a conventional multiband pulse for excitation in a gradient echo sequence. For comparison, the images were acquired using a 3D readout and a slice accelerated 2D readout. Both the 3D images and the single slice images separated using the slice graph algorithm show the center brightening artifact caused by the inhomogeneous B1 plus field. The measured flip angle maps, which match well with the predicted map, show overflipping of spins in regions with higher B1 plus value. The bottom part of the figure shows the acquired images and maps measured using the proposed multiband spokes pulse excitation. The separated slice images show a visibly reduced center brightening compared to the images from the conventional multiband excitation. The separated slices match well with the images acquired using a 3D readout. More notably, the measured flip angle maps show significantly reduced flip angle variance in all the slices compared to the conventional excitation, as predicted in simulations. To summarize, in this work we have proposed multiband spokes pulses to mitigate the effects of transmit RF field inhomogeneity in high field MRI. We have demonstrated that images acquired at 7T using the multiband spokes pulses show significantly reduced center brightening artifact compared to images acquired using conventional multiband excitation. The multiband spokes pulses will be most useful for high field SMS applications such as functional MRI, diffusion weighted imaging, and susceptibility weighted imaging.